The main focus of Chapter 3 overall is to talk about how to take the derivatives of different types of functions. So right now we really only know how to take the derivatives of polynomial functions and then some simple root and rational functions using the power rule. But in this chapter we're going to look at all sorts of different types of functions and all sorts of different derivative rules that'll help us find derivatives of more complicated functions. So we're going to start off with the exponential function here. It says the derivative of f of x equals e to the x is, well, f prime of x equals e to the x. So this is a really neat function in that the derivative is the same as the original function. If I take the derivative of e to the x, it doesn't change. It's still just e to the x. Remember that e from the last section, e is a constant. It's an irrational constant, so that means it's an infinite decimal that doesn't end or doesn't repeat. But e is just a constant. It's 2.718 ... and it just keeps going forever. So here the big difference here is rather than have x to the nth power, which is what we're used to seeing with the power rule, now instead I have my constant is e and x lives in the exponent. I've sort of switched where my constant and where my variable live. And this will only work, I should say, for this particular constant if we have e. If that number changes, we can still take its derivative, but the derivative will look a little bit different. And we'll talk more later on in this section. So I want to look at a few examples here. While this derivative is simple, it's about as simple as it gets because the derivative doesn't actually change the function. But it's so simple that it can be easy to throw in some trick questions and to make silly, easy mistakes. So I'm going to walk through a few examples here to hopefully show you those, and so we can learn how to avoid them. So the first function I have here is f of x equals e to the x plus 5x cubed minus 2x. And this first term right here, e to the x, well, that looks exactly like the exponential function that we were given the derivative formula for. The derivative of e to the x is e to the x. So when I take the derivative here, when I start to find f prime of x, well, the derivative of this first term, e to the x, is just e to the x power. After that, the other two terms over here, the plus 5x cubed minus 2x, well, we know how to take the derivative of those terms. We can just use our power rule for that. So we should have plus 15x squared minus 2. And there's our derivative. There's nothing else we really need to do in that case. So that's kind of the nicest, easiest, simple case that we're going to run into. In the next example, part B, here I have f of x equals x to the 7th power minus x to the 5th power plus e to the 3rd power minus x plus e to the x. I think there's two common mistakes that you can make on a problem like this. And the term I'm kind of looking at that's going to be tricky for us to deal with is this one. It's e to the 3rd power. Now, one way we can make a mistake, the first few terms, we know how to take the derivative of those. We're just going to use our power rule. So even before I start, I could say, okay, for my first two terms, f prime of x, that's 7x to the 6th power minus 5x to the 4th power. So at this point, we're thinking about the power rule, and we're kind of in a rhythm here. It can be easy to say, well, I'm just going to use the power rule right here and say, okay, well, the derivative of e to the 3rd is 3e squared. But that, unfortunately, wouldn't be right. We need to be careful here because what makes this term different from the other two, here the base of our exponent was x. It was the variable, it was the variable that we're taking the derivative with respect to. Here, my base is e. Hey, remember e we said at the very beginning of this is a constant. It's 2.718. If I think about the derivative of e to the 3rd, well, even just e to the 3rd, let's not even worry about the derivative quite yet. If I were to think about what e to the 3rd looks like, that's 2.718 ... all of that raised to the 3rd power. Now, if you wanted to, you could go and grab your graphing calculator and you could figure out, what exactly does this number look like. But 2.718, that's a constant. If I raise it to the third power, that's still just going to be a constant. So at the end of all this, this is going to be, well, a constant. And, well, what do we know about the derivative of constants? The derivative of any constant is 0. So e to the third is actually just a constant. It just looks a little bit different. So we need to be careful. We need to kind of be on the lookout for terms that look like this. So when I go to take the derivative of that third term, when I take the derivative of e to the third, I should really have plus 0. Now, you don't necessarily need to write in that plus 0. You could just skip that term and move on. But I want to include that plus 0 just to really emphasize that the derivative of that third term is 0. One other common mistake I just wanted to point out, e to the third, be careful here. This kind of maybe looks like e to the x, but it's a much different function than e to the x. It's e to the third power. It's not e to the x. So another mistake we might make is we might also say, hey, the derivative of e to the third is just going to be e to the third. Well, that's not the case because we said e to the third is a constant, so its derivative is 0. So that's the trickiest term to deal with. The other two, the last two, shouldn't be as bad. Here, the derivative of negative x, that's going to be -1. And then the derivative of e to the x, well, we talked about that already. That is just, well, e to the x when we take its derivative. So we can leave our answer like this, or if we want to rewrite it without the 0, you can say f prime of x is equal to 7x to the 6th power minus 5x to the 4th minus 1 plus e to the x. And there is my derivative. So anytime we have e raised to a constant power, its derivative will be 0. So it's just something that we're going to have to keep an eye out for. Our next example, f of x equals 4e to the x minus 7x squared plus 1 over x. This term, I think, is going to be the trickiest one. It's a little bit new here, so we'll talk specifically about that one in just a moment. The other two terms, I do know how to take the derivative of. -7x squared, that's going to be a power rule. No problem there. But 1 over x, we will have to rewrite using our exponent rules. So before I do anything else, I'm just going to take a step to rewrite this function as 4e to the x minus 7x squared. And that last term I'm going to write as plus x to the -1 power so that I can use my power rule in the next step. So I haven't actually taken the derivative. This is still f of x. My next step, however, I do want to take the derivative. I want to find f prime of x. First, I need to talk about the derivative of 4 times e to the x power. And this can be really tricky. It's easy to mix up. And here, let me erase this so that I have a little bit more room over here. It can be easy to mix up 4 times e to the x with 4 plus e to the x. This, I think, is where our brains maybe go naturally, or at least some students will make this mistake, so I want to talk specifically about it. 4 plus e to the x, that's different than 4 times e to the x. So 4 plus e to the x, yes, when I take its derivative, would be 0 plus e to the x. But when I take the derivative of 4 times e to the x, well, that's going to look a little bit different. And in order to think about that, let's just think about as a function that we know how it behaves. Okay, if I were to take the derivative of y equals 5x cubed, we know that derivative looks like 15x squared when we take the derivative. But what's really going on is we're saying y is a constant function, or excuse me, 5 is a constant multiple. So we would say 5 times the derivative of x cubed is 3x squared, and that's really how we get 15x squared. So what happens with constant multiples is we just multiply the derivative of our function by that same constant multiple. So I can look at the derivative of e to the x, well, that's just e to the x, and then this constant multiple of a 4, well, I'm just going to multiply my derivative by 4. So the derivative of 4e to the x, the derivative of 4e to the x will just be 4e to the x. The other two terms, like I said, we can use our power rule, just like we normally would. So here I have minus 14x to the first power. That last term, we'll have to be careful. We've got minus 1x to the negative 2 power if we use our power rule. I'm just going to rewrite that last term because I like positive exponents. So our derivative should look like 4 times e to the x power minus 14x minus 1 over x squared. And here's our derivative. Our last example here, f of x equals 3 times x to the e power minus 2 times e to the x power plus e to the fourth power. So this is kind of putting both of the, or really all three of the common mistakes that I think we could run into within this problem. We've talked about these two already. This first one's kind of new. It says 3 times x to the e power. We're used to seeing something like 3 times e to the x power. You kind of know what that looks like. We just talked about an example like that right before this. 3 times x to the e, remember though, hey, e, that's just a constant, 2.718. So here I have x being raised to a constant power, which means, well, I can use my power rule there. So if I think about what my power rule says, I multiply by my power, so we'll have 3 times the power, in this case the power is e, times x, and then we subtract 1 from the exponent. So if I subtract 1 from e, I could go and get a decimal approximation, but I don't like to use that. I'm just going to say, well, that's just e minus 1, because that's subtracting 1. The remaining two terms, those we hopefully have feel a little bit more confident about. The derivative of negative 2 times e to the x, well, the derivative of that term, derivative of e to the x, is just going to be e to the x. And then we also multiply that by our constant multiple of 2, so we should have minus 2e to the x for that second term. E to the fourth, remember e is a constant, 4 is a constant, so e to the fourth, also a constant. I'll make a note of that. So that last term, its derivative should be 0. So for this last function, its derivative should look like 3 times e times x to the e minus 1 power minus 2 times e to the x. So while this is a relatively simple derivative rule on its own, we do have to be very careful with different ways that we can kind of manipulate the equation to look similar to cases where we might use the power rule or something else. We just need to be very, very careful and very, very aware of what our functions look like so we don't make those kinds of mistakes as we're working with this derivative.